Today I want to talk something about Internet Explorer exploiting. IE exploit is not a new topic. It has been discussed for many years, so why IE exploit again? As you may know, starting from last year, Microsoft has added many exploit mitigations to Internet Explorer. And also the latest OS have a new exploit mitigation known as control flow guard. So it is a good challenge to try to bypass all these mitigations to make working to make a working exploit on the latest platform. So that's why I'm here. This is today's agenda. After a short self-introduction, we were starting with new IE exploit mitigations, including the isolated heap, deferred free, and the control flow guard. For each mitigation, I will first have a brief introduce to let you know how it works. And then we will discuss how to bypass it. And finally, we want to talk something about exploit 64-bit IE. There's some difference between exploiting 32-bit IE and 64-bit IE. I'm from the 316 Vulkan team, and basically we do system security research, and we have just successfully exploited Internet Explorer 11, the 64-bit with enhanced protected mode, as well as the latest EMAT tool. So I think it's a good timing for me to speak IE exploit here, since we have just finished the contest and the stuff is still in my mind. We are not going to talk about the 0-day we used in Pontoon, but we will introduce some method we use to bypass the latest exploit mitigations, which were also used in our Pontoon exploit. I have several years of experience in security research, and I'm interested in bug hunting and exploit developing, as well as anti-malware solution development. I'm also a hardcore ACG otaku, and I love Japanese comics and animations. Yeah. So this is my main job, watching animations and comics, and I also do security research to make a living. Yeah. So, okay, let's start today's topic. First, we will start with the new use after free exploit mitigations in IE. These years, we have been seeing many 0-day exploits exploited in the wild, and most of them are use after free bugs. So I think that's why Microsoft decided to add some use after free mitigations to the Internet Explorer. This is a typical IE use after free exploit. Basically, it consists of 4 steps. First, an object, the UAF object, will be allocated on the heap. And the second, because of the bug, the object will be freed unexpectedly, and while there is still some reference to this object exists. And the third step, the attacker will try to allocate some other objects. Usually they use string objects to control the memory of the freed object. And then finally, attacker will try to access the freed object again. And for example, they will control the virtual function table of the freed object and issue a function call on this object by doing this, the attacker can control the execution flow to where he wants. So it's not difficult to notice that the key point of a UAF exploit is that the attacker must be able to control the content of the freed object with the content they want. So both of the two new IE UAF exploit mitigations focus on making this control step harder. Let's see how they do it. The first one, called the isolated heap, it tries to isolate the heaps used by the high-risk objects with other objects in IE. So what are high-risk objects? These objects are they are objects that are easily accessed and manipulated with HTML and JavaScript code. And they are also the most affected objects by UAF bugs in the wild. For example, the DOM elements, tree node, tree process, markup objects, and some of the rendering objects are all high-risk objects. And now these objects will be allocated in the isolate heap, which is here, the H-isolate heap in MS HTML. So isolated heap tried to stop UAF exploits at this step, the control step. Now, one attacker tries to control the content of the freed object. They will have less choices because they can only use objects in the isolated heap to do this. So before isolated heap mitigation, UAF exploits often use string to control the content of the freed object. For example, we have a DOM element here, which is the C image element. After a C image element is freed, attacker will allocate a string with the same size with the C image element. Then it can control the content of the freed object. This is it is possible because both C image element and the string object is allocated in the same heap, which is the process heap. And now with isolated heap, we cannot do it anymore because now C image element will be allocated on the isolated heap, while string object sorry. So isolated heap is very useful mitigation. For elements allocated in isolate heap, you cannot easily control its content after it is freed. And the next mitigation is the deferred free. It can be described like this. When an object is freed, the memory of this object will not be freed immediately. Instead, it will be added to a list, which we call the deferred free list. And each thread has its own deferred free list, which is maintained by the class called memory protector. And later, the memory protector will go through the deferred free list and try to try to free the heap blocks in the list. And for each block in the deferred free list, memory protector will try to check whether it is safe to free this block now. For example, for object with the address X, memory protector will try to search on the stack to find whether there is a value which equals to X on the stack. And if such value is found on the stack, then memory protector will consider that this heap block is not safe to be freed now. The reason behind this check is that if we can find a value which equals to address of the heap block to be freed, then it is probably a reference to this object. So after this object is freed, it might be accessed by this reference again, which causes use after free issue. So to avoid such risk, memory protector will not free this heap block. This is an example. We have two objects, object A and B, and we free them, and they will be added to the deferred free list. And when the memory protector tries to free the blocks in the list, first it checks the object A, whose address is X. And in our example here, because there is a value which equals X on current stack, so memory protector will not free object A. And for object B, whose address is Y, because there's no value equals to Y on current stack, the heap block will be freed successfully. As we can see, deferred free mitigation tries to stop UAF exploits at the first step by not freeing memory blocks, which may potentially cause UAF issues. So if there is no free, there is no use after free. I think guys in Microsoft are very clever, and maybe one day it becomes common that every computer has thousands of gigabytes RAM, and we can just simply not free any memory blocks. And maybe we can say goodbye to UAF exploits at that time. Yeah. So same as isolated heap, it's the deferred free is very efficient. And Microsoft saved a lot of CVE IDs with this mitigation, because now if your UAF bug cannot bypass the deferred free, Microsoft will not consider it to be a security bug. It's a bit weird, I think, because the bug itself still exists, right? Okay. So we have introduced how isolated heap and deferred free work. They are indeed very powerful mitigations, but UAF exploits will not disappear. There are still many objects that are not allocated in the isolated heap and deferred free. And even if the object is in the isolated heap and deferred free, there's still some method to exploit them under certain conditions. And we will give some examples. Microsoft, I think this guy from Microsoft thinks this mitigation can kill UAF exploits, but actually not. Yeah. To exploit UAF bugs with deferred free, the key point is to avoid reference to the UAF object on the stack. Basically, whether you can avoid such reference on the stack is decided by your bug itself. But sometimes a UAF bug seems not able to bypass deferred free. But if you adjust your POC to let the object to be freed in another code path, and maybe there will not be any reference to it. To be able to adjust your POC in this way, you must have a deep analysis on your bug to understand the root cause, and maybe you can adjust it. Here is an example of a patched UAF bug. When it is found in our fuzzer, it will immediately crash when executing the statement document.write uKey. It crashes because when the object is freed by the deferred free, the memory of this object will be cleared to 0, and later when it is accessed again, it crashes due to a null pointer dereference. And we can adjust this poke like this. We add a reference to this object first. So when executing the statement document.write, it will not be freed immediately, and we can avoid crash. And later, we let it to be freed in another code path, and we can use this bug to achieve code execution. Now let's discuss how we can exploit UAF bugs under isolated heap. For objects allocated in isolated heap, we can only use objects in the same heap to control their content. Basically, we have two choices. The first one is to use object with the same size as the freed object. And the second is we can use the object of different size with the freed object. As you can see in this picture, the first method is reliable because both of the object size are equal, and but if you use same size object, the number of objects we can use is limited. And using different size object may be unreliable because we need to lay out the heap accurately in order to be able to control the field which we want. However, we can have more choices. We can have more candidate objects to use. So although the different size objects approach is unreliable, we still recommended it in practice because here more choices is more important. And here's another thing you have to know to exploit UAF bugs under isolated heap, which is the low fragmentation heap, or LFH in short. LFH is designed to reduce the fragmentations in heap allocation. LFH will try to allocate same size objects together. For example, if we allocate two objects with size x and y, where x and y not equal here, when LFH is not enabled, the two objects might be allocated together near each other. And if LFH allocation for size x and y is enabled, they will be allocated in their corresponding buckets. And basically, they are not allocated together. So if LFH for a size x is enabled after a block of size x is freed, we are not able to use another block of size y to control the content of this block unless you free all blocks, all LFH buckets in the big LFH block that contains x. And on Windows 8.1, because of the front-end randomization of heap allocation, it's also very difficult to control accurately, even if you free all the buckets here. So if we want to use different size objects to control the content of the freed object on Windows 8.1, what we need here is to avoid the LFH for the UAF object. Yeah, we have to avoid LFH. When an allocation request of size x comes for the first time to a heap, the array fetch for size X is not enabled yet. And array fetch for size X will be enabled only when the number of allocation requests for size X exceeds some threshold. So if we keep our exploit code as simple as possible, we can avoid array fetch before we finish the control. So basically, we need to postpone any operations that are not necessary for triggering the bug. Look at these two web pages. The first one is very simple. We just created one CImage element. So when this element is created, it is highly possible that its memory is not allocated in LFH. So we can use object with different size to control it after it is freed. And the second one, the code will try to allocate 100 CImage elements first. So this is enough to trigger the LFH to be enabled. And when we allocate next CImage element, it will be allocated in LFH. So it's very difficult for us if we want to control its content, use different size object. Now we will give you a real example of exploiting a UAF bug under the isolated heap. It is a use after free bug in CImage element. Our father found this bug in August last year, and it was patched in October. First of all, you need to know that all image elements in the same document are linked together using a double linked list as shown in this picture. This is our POC, which is not important here. And the effect of our bug is that we can make a CImage element to be inserted into this list for more than once. So even after the CImage element is freed, the list entry for it will still exist in the double linked list. And we can access this element by visiting the list. Okay, now we can access an image element after it is freed. So to exploit this bug, we need to control some fields of the freed CImage element. Which field to control? As we mentioned before, CImage element is linked into a double linked list, and the offset 0x44 is actually the structure of a list entry, which is used to link the image element into the list. And if we can control the content of this list entry, we can do something interesting. And how to control the list entry in the freed CImage element? Because it is allocated in the isolated heap, so we can only use objects in the isolated heap to control it. And the object we choose must have at least one field whose value is controllable by us. There are some choices. For example, we can use the CSTR string. The CSTR string is often used in DOM elements, and it points to a wide char string whose value is basically controllable by us. For example, if you create a C generic element here, we can control two CSTR strings in this element. And also other DOM elements contain CSTRs too. So here we choose the C generic element to continue our exploit. The reason we choose it is that the list entry structure contains two dwords, and using C generic elements, we can also control 2 CSTR strings, which is also 2D words in size. It's perfect for this bug. The next step is to lay out the heap accurately to use the CSTR strings to control the list entry. After the C image element is freed, finally the heap block of this element will become part of a big freed block here, whose size is 0x998 here. And there is 724 bytes between the beginning of the free block and the list entry field in the freed image element. And by simple computing, we decide to lay out the heap like this. First, we allocate 3 C video elements, following by 3 C HTML canvas elements. And at last, we allocate a C generic element and control the value of the 2 CSTR strings in the C generic element. And with this layout, you can see we can accurately control the list entry in the freed C image element. And after control the list entry of the freed C image element, we can reach some code that can write arbitrary memory. And finally, we can achieve remote code execution. Here are some key points of this example. First, we achieved full remote code execution with a UAF bug, which is allocated in the isolated heap. And we use CSTR strings to control the field we want. There's other choices you can use. For example, you can use CUDS field in a C area element. And in order to let this approach work, we need to avoid LFH on Windows 8.1. And finally, there exists some patterns for different objects UAF. For example, for a tree node UAF, which field to control and which object we can use to control. Yeah, you can think after the topic. And the biggest problem of this method is that we have to avoid LFH, which means we need the heap state as clean as possible. If the user has already visited several pages before navigating to our exploit page, then we are very likely to fail because the LFH might have already been enabled during the previous navigations. So the best way is to start a new IE or use a clean tab to open our exploit URL. If we always need to start a new IE or a new tab, you may doubt that whether it is useful in real world. The answer is yes. You know, there are many applications that can contain URL links, such as Microsoft Word, Office, Word, PowerPoint, and Outlook, and some instant message applications. And when you click the URL links in these applications, the default behavior is that a new IE or a new tab will be opened to visit our URL. And now we will give you an example of a zero-day UAF bug in isolated heap using this method we introduced above. Let's start the virtual machine. This bug is UEF in C option element, which is also in the isolated heap. And you can see there is a link, and if we click the link, a new IE will be started, which gives us a clean heap state. You can see the calculator pops up. You may think it's very complicated if you want to lay out heap like this, but actually it's very reliable because the objects in the isolated heap are limited. They have a very limited number, so the heap is very easy to lay out. Okay, so if you want your exploit to work on the latest OS, for example, Windows 8.1 or higher, there's another new exploit mitigation that you have to worry about, which is a control flow guard, or CFG in short, which is also a very useful mitigation. CFG is a new mitigation introduced in Windows 8.1 update 3. And the purpose of CFG is to prevent unexpected control flow change in indirect call. So what is an indirect call? For example, the virtual function call in C++ objects is indirect call. And in assembly code, you can see a virtual function call looks like this. First, we get a virtual function table from the object, and then retrieve a virtual function in the table. And finally, we call this function. And exploit writers often tries to overwrite the virtual function table to control the execution flow to somewhere they want, usually some shellcode or ROP gadgets. And the CFG will try to stop this control flow change by checking all target address in the indirect calls to make sure they are valid. Let's see how it works. Suppose we have an indirect call here. The target address is 112233. And before call into this address, CFG will check this address in a bitmap, which is maintained by CFG. The bitmap contains all valid call targets, all valid indirect call target addresses. So if CFG can find that this address is a valid indirect call target, then it continues to call this function. But if it finds it is not a valid call target, then it will raise an exception and the current program will be terminated. When CFG is not enabled, attacker can control the virtual table and jump to, for example, some ROP gadgets. But when CFG is enabled, it will check whether this target address is valid. And because some ROP gadgets address is not valid indirect call targets, so the exploit can be stopped by CFG at the wrong time. This is the exception raised by CFG check. We can see CFG is really a very useful exploit mitigation, but it still has some weaknesses, and there's several ways to bypass it. Here we listed some methods we may use to bypass CFG, and we will discuss them in detail. First one, we can call valid APIs to achieve our purpose. As we introduced before, CFG has a bitmap which serves like a whitelist to indicate whether a function is a valid indirect core target. And many Windows APIs are in this whitelist. For example, WinExe, load the library, ZW continue. And if we overwrite the function pointer with these valid APIs, then we can bypass the CFG check. Here's an example to use load the library to bypass CFG check. In order to call load the library, we need to give a path to it. And we can use UMC path here. Here is the code we use to call load the library to bypass CFG. You can see we overwrite the virtual function with load the library A, and then we give the parameter to load the library A, which is the UNC path of our payload DL. And if you see this approach in a debugger, it will be more clear. First, the virtual function is overwritten by our load the library A, and then CFG checks whether load the library A is OK, and we bypass this check, and then we can load the payload into current process. And another kind of interesting API is API which can change the execution context of current thread. Execution context includes sets of registers, for example, the EIP, the stack pointer, eFlags, and such API allows us to set context of the thread, and by simply set, for example, set EIP in the context, then we can jump to anywhere we want without checked by CFG. Here we take this API long jump as an example. This is a C function which is often used in error handling. The first parameter of long jump is a structure called jump buffer. It contains some register values. You can see there's EIP, ESP in this structure, and long jump will change current register values to the new values specified in this jump buffer structure. And if we set the EIP field in the jump buffer, then we can jump to anywhere we want. We can see these context change APIs are very powerful. And to prevent abusing of these APIs for malicious intent, Microsoft had added some check in these APIs, which we called the stack pointer check. Take the long jump as an example. At the beginning of the API, it will check whether the ESP register specified in the jump buffer structure is in the range of current stack. If the ESP you given is not in the range of current stack, it will consider this call is to be an invalid call and will raise an exception. So if you want to use such APIs, the first thing you need to do is to leak a valid stack address. It's not difficult to find a stack address. There are several methods to do this. For example, you can search it in loaded modules or in global local data structures, or you can search it in a brute force way. Or you can call some APIs that can give you current register values. To find a stack address in loaded modules, you only need to write a simple script to go through all loaded modules and find out whether there's some stack values. Here is the output of our script. You can see there's some stack address in the JScript 9, which is also used in our Pong2On exploit. And some global local data structures in IE may also contain stack addresses. For example, the memory protector, which is used which is used in the deferred free mitigation, will store stack pointers. And if you already have the ability to read the full user space memory, then you can consider to use a brute force way to search for a valid stack address. And you can first search the thread environment block structure in current thread, because there is a stat limit and a stack base in TEB. To do the brute force search, we need to avoid crash, and we can use some APIs such as is bad code PTR to check whether a page is readable before we read the content of this page. This way is reliable and independent of the module version. Some Windows APIs can also give you stack pointers. For example, the setJump API or getThreadContest. The next method to bypass CFG is to overwrite direct call instead of indirect call. Because CFG only checks indirect call, we can use direct call to jump to our shellcode or ROP gadgets. For example, we can use function address in imported tables, or overwrite some global function pointers or local function pointers. Here is an example of overwriting a function pointer in a JavaScript function object. You can see there is no CFG check here, and basically we directly jump to anywhere we want. And if you already find some stack address, and if you have ability to write the stack, then you can simply overwrite the return address or put your ROP on the stack. CFG aims to stop the unexpected execution flow change, but if your exploit does not require such execution flow change, then we do not need to worry about CFG. For example, we can use a safe mode in IE, and then use some ActiveX controls to do the follow job. And the last one, we can use legacy modules which are not compiled with CFG to bypass the check. It is possible because CFG is a compile time mitigation, and the compiler support for CFG only exists in the latest IDE. So many legacy modules or third-party modules are not compiled with CFG. Even the emet tool itself before version 5.2 does not compile with CFG. Microsoft just fixed it before the .1 test. Here is an example of using the module in Java runtime environment to bypass CFG. It is not compiled with CFG. So you can see we can just pass the check and jump to anywhere we want. Last, we want to talk about something about 64-bit Internet Explorer. There's some difference between 32 exploit and 64-bit IE exploit. For example, heap spray, you cannot directly use heap spray in 64-bit IE, and the memory read-write method may be changed. And also the call convention in 32-bit and 64-bit are different. On 64-bit IE, heap objects address use 40 bits, and a module address will use 48 bits. What does that mean? On 32-bit IE, a heap spray of 500 megabytes memory is enough for us to get some objects. But on 64-bit IE, you may need to spray more than 100 gigabytes, which is infeasible here. Although the direct heap spray does not work on 64-bit IE, a relative heap spray is still possible. It is because although every heap's address is randomized, object's address in the same heap is still predicatable. So if you spray a lot of objects in the same heap and then leak one of the objects, then you can use the leaked address to get another object address which you want to operate. We also use this trick in our Pontoon exploit. And the next difference is when we try to read-write whole userland memory space, on 32-bit, corrupted string or JavaScript array is enough to do this. But on 64-bit, you cannot read backward or forward beyond the 4 gigabytes memory, as shown in this picture. Because JavaScript array's length field has only 4 bytes, so you cannot use it to read backward or forward beyond the 4 gigabytes. So to read the full memory space, you may need to overwrite the pointers in the string object or overwrite the pointers in the array object to do this. And the last one, the call convention are different in 32 bits and 64-bit IE. On 64-bit, the first 4 parameters of STD call are parsed by registers, while 34-bit use stack to pass parameters. So in 64-bit exploits, you may not need to worry about the stack balance because most parameters may be passed by registers. And also, the call convention will affect your shellcode and ROP. Okay, so today we introduced the new exploit mitigations include isolated heap and deferred free and CFG. Although they are very useful mitigations, there is still some method to bypass them and make a working exploit under these new exploit mitigations. And finally, I want to thank to Mr. Thomas Lim and guys in 316 Vulkan team. Thank you.